Assalamu alaikum. The subject of this course in advanced pharmaceutical analysis. By using different spectroscopic technique, we can identify or determine the chemical structure of organic compound. This spectroscopic technique involves four major types, which include ultraviolet spectroscopy, give idea about electronic transition, and give idea about electron bonding in the molecule. The second type, infrared spectroscopy, which used to determine the functional group present in the molecule. Third, mass spectroscopy, it break molecule into fragment, and we can use this technique to know the molecular weight of organic compound, and when we close the fragment to each gather, we can give idea about the structure of the organic compound. Finally, nuclear magnetic resonance spectroscopy, which help and observe the chemical environment of the hydrogen or carbon atom on the molecule, so can be provide map of the atom in the molecule. First, we start with nuclear magnetic resonance, also called NMR. The use of NMR spectroscopy. NMR spectroscopy used to determine relative location of atom within the molecule. It's most helpful spectroscopy technique in organic chemistry related to magnetic resonance imaging, and give map of carbon-hydrogen framework of the molecule. It depends on very strong magnetic field. So by NMR can take idea about the distribution of carbon and hydrogen in the organic. The H1, also called the proton and carbon 13 nuclei, have a spin. In other words, behave as if they were spinning about an axis. This will produce a magnetic interact with an external magnetic field. Magnetic nuclei include all nuclei with an odd number of protons, such as H1, H2, nitrogen 14, fluoride 19, phosphorus 31, and so on. Or nuclei with an odd number of neutrons, such as carbon 13. Non-magnetic nuclei include nuclei with even number of proton and neutron, such as carbon 12 and oxygen 16. And the following table give example for the type of magnetic nuclei and non-magnetic nuclei. In the absence of external magnetic field, magnetic nuclear spin are oriented randomly as shown in the following figure A. But in the presence of an external field referred to P0, magnetic nuclear spin oriented with parallel to or against, also called anti-parallel to the external, as we show in the following figure B. Pink color parallel to the applied external field, while blue color anti-parallel to the applied magnetic field. The orientation of nuclei response to the applied magnetic field depend on the energy of each nuclei. A nuclei with slightly lower energy will be oriented parallel to the applied, while nuclei with higher energy oriented anti-parallel to the applied magnetic. Anti-parallel, the exact frequency necessary for resonance depend on two important factors. First, the strength of external magnetic field, and the second, the identity of the nuclei. the exact frequency necessary for resonance is proportional to the field strength. In the absence of applied magnetic field, spin states have equal energy, while in the presence of a magnetic field, spin states have unequal energy. If a very strong magnetic field is applied, the energy differences between the two spin states, delta E, is larger, and higher frequency radiation is required for spin flame as showing in the following figure. The nature of the Nmr absorption. The absorption frequency is not the same for all proton or carbon-13 nuclei in the molecule. This will depend on the type of adjacent functional group. All nuclei in molecule are surrounded by electrons with their own magnetic field. This magnetic field resulted from spinning of electron called local magnetic field. When an external field is applied to the molecule, the effective field, mean the field will cause flip of the nuclei, is a bit smaller than applied field. So effective field equal to applied field minus local field. Nuclear magnetic resonance spectrum. Nmr spectrum plot the effective field strength felt by the nuclei x-axis versus the magnitude or intensity of Nmr resonance signal corresponding to the intensity of the energy, and this is y-axis. The intensity of the Nmr resonance signal is proportional to the molar concentration of the sample. This means if molar concentration used high, the intensity of the signal will be high and vice versa. Each peak in the Nmr spectrum corresponds to chemically distinct proton or carbon-13 in the molecule. Proton or carbon-13 spectra cannot be observed in the same spectrometer because of the difference in the energy required to spin flip the nuclei. This figure shows the two types of NMR. H1 NMR spectrum, the upper figure, as we see the x-axis measured by part per million and give idea about the chemical shift of the proton in the molecule, and graduated from 0 to 10, and now they also reach to 15, while the y-axis give the intensity of the signal. And the below figure give C13 NMR spectrum for the same compound, but we see there are two differences from the upper. At first, the x-axis also measure part per million, also give idea about the chemical shift, but it starts from 0 to 200. This difference is due to carbon atom larger than protein, so need higher energy to flip when we apply it external magnetic field. Also, the y-axis give idea about intensity. Other differences in the upper figure give two signal because two type of proton, while in the below figure give a three signal because three type of carbon present in the compound. Now, how we can determine the nuclear is a spin or not? This depends on the nuclear spin quantum number referred to I, which equal to n divided by 2. According to this, atom divided into two subtypes. First, called fermion, when the mass is odd and the number of proton also odd. So such type of atom have a fractional spin. Example: proton, carbon 13, fluoride 19. Other type, I equal to 3 divided by 2, such as boron, sulfur, and so on. Second type, called bosons, when the atom have mass equal to even, while number of proton is odd. So such atom also have spin, such as hydrogen 2 and nitrogen 14. Other type of bosons, when the atom have mass equal even and have even number of proton, so nuclear spin to quantum number for such type of atom equal to 0, so cannot be used in NMR, such as carbon 12, oxygen 16, or sulfur 32, and so on. Now, energy differentiation. In the presence of external magnetic field, two spin states exist, referred to as plus half and minus half. The plus half state is elegant with the external field, or in other words, nuclei with lower energy, while minus half spin state is opposite the external field, or in other words, nuclei with higher energy. Hydrogen isn't magnetic, but in fact the nucleus of hydrogen atom has a very weak magnetic spin. If molecule containing hydrogen is placed in a strong magnetic field, the magnetic hydrogen nucleus can line up with the field or line up against it, as shown in the following. First, nucleus spin elegant with the field. This nucleus characterized by low energy, while below, nucleus spin elegant against field because it has high energy. Now, how the nuclei can be undergo resonance? If nuclei with low energy affected by applied magnetic field, it will be absorb energy and transfer to excited state characterized by high energy. But when the source of applied magnetic field stop, the nuclei release energy and back to lower energy state. The energy released can be used to give idea about the environment of hydrogen in the molecule and how many hydrogen atoms are in that environment. This figure shows the constituent of the Nmr spectrometer, which consists from different parts. Consists from magnet, which control by magnet control, also contain part for sample, and detector and transmitter, where from this we can record the differences in energy and appear as a signal. من هذا السلايد راح نبدي او تبدي المواضيع المهمة اللي حوالين ال NMR. عندنا information from H1 NMR spectra. First, number of signal, او بمعنى كم بيك تظهر عندنا بالسبكترم of NMR. هذه الحالة number of signal give idea about how many different type of hydrogen in the molecule. كم نوع من الهيدروجين اللي مختلف موجود عندنا مركب. Second, position of signal اللي also called chemical shift give idea about what type of hydrogen ينطينا فكرة عن نوع الهيدروجين. 3. Relative area under signal also called integration give idea about how many hydrogen of each type يعني كم هيدروجين عندنا بتكون متشابه. يعني النقطة الأولى مثل ما ذكرنا راح يكون عندنا different type of hydrogen كم نوع من الهيدروجين مختلف. النقطة الثالثة راح تعطينا فكرة بالسيجنال الوحدة كم هيدروجين عندنا، أو بمعنى آخر الهيدروجين المتشابه إيش قد موجود عندنا بالمركب اللي دندرسه. 4 point splitting pattern how many near boring hydrogen. هنا راح يعطينا فكرة عن عدد الهيدروجين المجاور للهيدروجين اللي انطانا البيكو. ان شاء الله هذه النقاط راح ناخذها in detail خلال المحاضرة والمحاضرة القادمة. Now we start with the first information can be obtained from Nmr spectrum. First point, number of signal. Give idea about how many different type of hydrogen in the molecule. In other words, non-equivalent proton. Magnetically equivalent hydrogen resonate at the same applied field. Magnetically equivalent hydrogen are also chemically equivalent. What are mean by equivalent hydrogen? This means these hydrogens have same properties. For example, number of signal in the methane 1. Ethane also number of signal 1. Why? Because the 4 hydrogen in methane are equivalent. Also, all hydrogen in ethane 6 hydrogen are equivalent. So we'll give 1 signal. Now, when the hydrogen will be non-equivalent, we take the following example. The environment of hydrogen atom in the acetaldehyde. The frequency of energy needed to flip the magnet or spin in different hydrogen atom are in different position. For example, the hydrogen linked directly to the carbonyl group need higher frequency energy to flip here. So high frequency energy released when it flip back, while hydrogen bind or linked to carbon flip quite easily, so need low energy frequency. So there are 2 types of proton or hydrogen in acetaldehyde, so give in 2 different positions. In the proton Nmr of acetaldehyde, we see 2 peak or signal. This due to this compound have 2 non-equivalent hydrogen. 1 hydrogen bind to the carbonyl and 3 hydrogen bind to the carbon. The 3 hydrogen bind to the carbon are equivalent, but it's non-equivalent to the hydrogen bind to the carbonyl, so the spectrum show 2 signal. Another example, first butene. Spectrum of butene show appearance of 2 signal due to the compound have 2 type of hydrogen. 1 hydrogen linked directly to the carbon double bond, and other type of hydrogen bind to the terminal carbon. Other example, propanol alcohol. The spectrum of propanol alcohol show appearance of 4 signal. This due to the compound have 4 different environment of hydrogen. 1 related to the hydrogen bind to the oxygen, and the other 3 of hydrogen bind to different of carbon. هنا الاختلاف ده يصير عندنا لأن الكربون اللي قريبة على الأكسجين تكون highly affected by electron activity of oxygen، وكلما ابتعدنا عن الأكسجين كلما تأثير الأكسجين راح يقل عندنا. لذلك الثلاث ذرات كربون أو الهيدروجين اللي مرتبط بالثلاث ذرات كربون اللي مجاورة للأكسجين راح تختلف عن بعضها، لذلك راح تظهر عندنا 4 signal. Another example, ethyl benzene derivative. Also the spectrum of this compound show 3 signal due to presence of 3 type of environment. First environment related to hydrogen bind directly to the aromatic ring. Second signal related to the hydrogen bind to the carbon adjacent to the aromatic ring. Third hydrogen related to the hydrogen bind to the terminal carbon. In the following example, the spectrum show appearance of 3 signal. 1 signal related to the hydrogen of methyl group that bind directly to the oxygen. The second type, proton of hydrogen B, for hydrogen linked to carbon between 2 carbonyl. And the third signal for the hydrogen bind to the carbonyl that in which bind to the carbonyl group. Now we take different examples to determine number of hydrogen in each compound. Compound 1, number of hydrogen 1, because cyclohexane contain 12 hydrogen, all of them are equivalent, while compound 2 also have 1 type of proton, or in other words give 1 signal in the Nmr spectrum because all proton are equivalent. Compound 3 benzene also show 1 signal, or in other words 1 type of protein because all the 6 proton will be equivalent, while compound 4 show 2 signal in the spectrum, or in other words 2 type of hydrogen. First hydrogen that bind to the aromatic ring, and the second hydrogen bind to the carbon of methyl group. In the following compound 1 show 1 signal because all the proton will be equivalent due to it equivalently affected by brom. Compound 2 show 2 signal because the proton that bind to the carbon bind directly to bromine, highly affected by brom, while terminal carbon that have proton, and this proton will be lessly effective by brom, so show 2 signal. Compound 3 show 3 signal, or in other words 3 type of proton because all type of proton will be effective differently by brom molecule. Compound 4 show 2 signal because have 2 non-equivalent proton, 1 proton that directly bind to the carbon carry out chloride, and the other 2 proton at the terminal methyl will be equivalent, so the compound show 2 type of proton. In the following compound 1 show 4 type of proton, so show 4 signal in the Nmr spectrum. Compound 2 show 2 type of proton, 1 that directly affected by chlor from each side, while the middle CH2 will be different from other type of proton, so the non-equivalent proton 2 type in this compound. Compound 3 show 3 different type of proton, one that linked directly to the aromatic ring, the other linked to the carbon of the methyl, and a third proton that linked to the carbon carry out chloride.